Welcome back to this section. We have now looked at the thermodynamic potentials and also the understanding that how statistical mechanics can help us go from microscopic properties into macroscopic world. And that essentially, by now it is very clear to you, is the main objective of the molecular dynamics systems to do multi-scale modeling. So, before we go further, I wanted to give you a crash course in statistical mechanics, and this kind of work was done in early 1900s by very famous scientists of that time, where they were trying to go away from some of the classical models to non-classical systems. So, Newtonian models have been existed for 300 years or so, and early 1900s then some of the theoretical geniuses like Einstein and Schrodinger, if you talk about Heisenberg, Niels Bohr, his son Age Bohr, all of them, it was kind of golden period of the development of new science and new what we now call modern physics. So, the ideas of statistical mechanics, quantum mechanics came in. Statistical mechanics predates quantum mechanics. So, when Schrodinger developed the famous Schrodinger equation, which was essentially a Hamiltonian equation to calculate the total energy of the system, he took a lot of ideas from the statistical mechanics, which existed before that time in about late 1800s and done by Maxwell, Planck, as well as we looked at some of the other major scientists who were involved in that, Willard Gibbs and likewise. So, if you look at the distribution functions and the statistics behind it, that was all generated there. So, what is the main theoretical framework of statistical mechanics, which later on was influencing quite a bit development of quantum mechanics. So, we will touch upon quantum mechanics, but not going into more detail, but let us understand the basic framework of statistical mech. So, if you look at the framework is created to essentially connect microscopic to macroscopic. So, in this world of statistical mechanics, first thing you talk about is microstates, and of course, the thermodynamics provided what is called macroscopic state variables, and those state variables were called temperature, pressure and volume, and some of the other like specific heat, bulk modulus, crystal lattice structure and lattice constant, as well as elastic constant. These were some of the parameters, and these were called macroscopic. So, these macroscopic calculations as well as experiments were done from continuum perspective, but there was no understanding of microstates and how that microstate leads to the macroscopic properties. So, if you look at the theoretical framework to connect macroscopic thermodynamic properties of a system with ensemble behavior, and we did talk a little bit about ensemble behavior of the microstates using statistical probabilities. So, now we went away from deterministic closed form solutions of the equations, which were the forte of the geniuses like Einstein and other Schrodinger, where they were always interested in creating some kind of equation, and which could explain a lot of phenomena. So, E is equal to mc square, which came out of the special theory of relativity. That was a one equation that explained a lot. And so, when the statistical formulation happened, some of these theoreticians did not believe in it, and that was one of the major issues with Einstein, who never believed as long as lived in the quantum mechanics, because it was based on the statistics. And one of his famous quotes was, "God does not play dice," came from this whole idea that he was in search of that one equation that can explain everything deterministically. But it so happened that quantum mechanics explained a lot of phenomena based on the statistical models and distributions that the classical mechanics was not able to explain, including the planetary motions and the gravitational forces. And that is where some of the changes that happened through the Einstein theory of gravity, and later on some of the same formulation on the space-time continuum when it happened in terms of the microscopic world. There was a similarity between what we call galactic world and the microscopic world. In fact, there was also Niels Bohr's thinking that the atoms behave almost like galactic world, where there is a nucleus which is like a sun and the earth orbits around it. Similarly, some of these electrons and protons and neutrons do that. But let me not get distracted, because we can go into a lot of details here. Coming back to it, the microstate of a system is defined by thermodynamic state functions. So, let us talk about state, and state functions are pressure, volume as well as temperature, and that is called state space, or we can also call it phase space, because a material will remain in a certain particular phase, like solid phase, liquid phase, gaseous phase, and that is defined by the state variables, and that is why this space is called phase space. So, if you look at these state variables allow us to define that phase space, and then what we want to do within that phase space, we want to create microstates. So, if you look at, let us say, atoms in a box, in molecular dynamics box, which we have been talking about it for last several weeks, that is creation of a microstate represented by a particle or a atom or a molecule like water molecule. That is the microstate that you are looking at. So, if you look at, it could be connected with the single particle states, or it could be molecular state, but you have to define a microscopic state that you are going to have, or microstatic microstate, where now you are going to look at that particle, and then you are going to average it over large number of particles in order to create what is called ensemble average. So, if you look at the microstates and the average, statistical averages, which connects with the probability distribution function, is very simple. A system can be defined as given in your slide as an ensemble of n microstates defined by I as one of the microstate, I going from 1 to n, and with a probability of pi. So, in this case p is not, do not confuse it with the momentum, but with probability I, and E as energy of that microstate, which is defined by I. So, if you look at the internal energy of a thermodynamic microstate, is a statistical average over all microstates. So, if you look at E, and if you look at this bracket which is defined here, so U is the internal energy, we understand that, is equal to average of energy of each particle and the probability that it occupies in the phase space. So, if you look at this is a summation of pi, I being 1 to n, and the probability distribution function, if you normalize it, it should come out to 1.0. But if you look at, there are lots of micro probabilities which are being summed over for each microstate called EI. So, you know their probability of existence in particular state space, and then you sum them up with the energy EI. If you average that also, it is almost like creating a mean, and in the statistical sense, and that is called internal energy based on the microstate of each atom. If you go further into entropy, which is what we define in terms of, if you remember, delta Q over T, or heat supplied over T, or you can even go further and say the S defined as Q delta Q over T. In this case, now we are going to define in terms of configurational energy of the system, which is connected with the order parameter. So, if you now look at S is defined with the Boltzmann distribution, and if you remember, we said very clearly that Boltzmann distribution tells us the velocity at which all the particles are distributed, and then if you take the logarithm of that pi ln p, logarithm of all the probabilities of these microstates, and then sum them up with the Boltzmann constant, that is the distribution of velocity, that will give you what we call as Boltzmann constant as the entropy of the system, which is a statement in the world of statistical mechanics as the second law of thermodynamics. So, the first one, U is equal to summation of I 1 to n pi EI, that is a statement of first law in the sense of microstates. The second one represents the second law of thermodynamics, which talks about the quality of energy, and that's related with the configuration of the particles and their velocity and the probability of finding those velocities on each particle, and multiplied by a distribution function, which essentially is a function which is exponential, and that gives you a entropy term. So, if you go further, let me define heat and work and internal energy. We also know delta U. So, in terms of statistical mechanics, heat is energy transfer to the disordered microstates, leading to increase in the energy level. So, and then if you look at work, is energy transfer associated with the ordered macroscopic action on the ensemble. So, think about, and we have seen this situation in our VMDL simulation, where we took bunch of particles in the gas phase, supplied heat to them and changed their phase, or took heat away from them by freezing them or melting them. In that case, we looked at the disorder microstate and leading to increase in energy level. We increase their energy level by supplying energy to that, or decrease energy level by taking away heat from it. In case of work, what we are doing external macroscopic action on the ensemble of particles. So, this is the piston in a cylinder, and you are moving that piston down with the pressure and temperature. So, delta W in the microscopic form, where there are n states of microstate, we have the Pi, again the probability, and DEI, which is the energy of is a particular microstate. If you sum them up from I is equal to 1 to n states, that becomes the total amount of work which is provided by the energy supplied to them through external macroscopic action. And in terms of providing the heat, you are looking at the energy which is provided in terms of heat multiplied by finding the probability function for them. And if you then combine the two, then you come back with the same equation, first law of thermodynamics, du is equal to delta W plus delta Q. So, this gives you connectivity now from where we are in the thermodynamics way in a macroscopic world, now connecting to the microstates into microscopic world. Thank you.